Good morning. Welcome to the garage door project. As you can see, I have a new intro video, or at least a new intro image. This is a bit of a homage to the outstanding work of Dave Jones on EEV blog. His EEV blog has over 700 videos on it, and he goes through a bunch of awesome information for people looking to work in the electronics field or build projects or just understand what's going on. It's one of my guilty pleasures is sitting in and watching his videos. And if you haven't been there, then I really, really recommend it. Awesome style, a lot of great information, a lot of great explanations. And you can go find that blog at www.eevblog.com. Fellow Australian, and I really can't recommend it highly enough. Anyway, what I wanted to do today was to start a short series, probably 2 to 3 videos, going through the component test harness that I've set up for the garage door project. And so what we'll do is we'll look at firstly the electronics, the hardware itself. Then we'll look at the software that I have to drive it, and then we'll look at the user interface that exists to go through that or to drive the individual components that underlie that. The first thing that I wanted to show you was the circuit diagram I put together for the garage door project. I had a chance to complete the test harness. As you can see in the image, I have the componentry laid out. It is all connected. I can now test all the core functionality and show it working. And so I created a test harness, and I wanted to create a schematic that represented the components that I have implemented on the project so far. So let's walk through the components here. The first thing that we have up here is an LM317. Now I'm using that to take the 5-volt rail or the 5-volt input that I have and step that down to 3V3. And the reason I'm doing that is that the LCD, the ST7565, is a 3.3 volt component. So I need to shift my logic levels down to 3.3 for that LCD display. So here we have a fairly standard implementation of the 317. I based the little design that we have here on the application note that was in the datasheet, and that's a great way of getting the core functionality that you need for the device. And so I have a ceramic capacitor across the input. I have the adjustment resistors set to output 3.3 volts here. And then I have a electrolytic capacitor across the output so that I get a nice, stable, clean 3.3 volt output. Now I take that and I share that both to the LCD and also to the level shifter. The level shifter that I had originally, if you remember a few videos back, was just a standard 4050 that Adafruit provided me as part of the purchase when I bought the ST7565. There was a problem with that, and I went through what it was, but effectively at the 3.3 volt level and the speeds that I wanted to run it, the SPI bus at, the 4050 wasn't able to reach the 3.3 volt output. So I went to DigiKey and I looked around, and I found a much faster 4050, part of the 74 class integrated circuits, and that enables me now to run the ST7565 and the SPI bus at the standard 4 megahertz that you would expect from an Arduino. Now I'm using a Galileo, but it's the same sort of standard. And so here you can see that I have the 4050 connected to the 3.3 volt bus, and this is a non-inverting level shifter. So I'm taking my signals in, and all of the control circuitry, the MOSI, the clock, enable, A0, and reset all go through the 4050 before coming out to the LCD. Now, the next thing that I wanted to show was just the LCD. It's hooked up on 3.3 volts for all of its data and control lines through that 4050. The LEDs, however, that provide the backlighting don't need to be at 3.3 volts. So what I have is I have those all just connected straight to the 5-volt rail. And I have a resistor that limits the current through those LEDs. So the background color that you get from that device is just the RGB being driven full. The next part that I wanted to talk about was the ultrasonic sensor. You would have seen me go through the various capabilities of this ultrasonic sensor, but it's an MB1040 from Maxbotics, and they're a great company to work with. And if you need an ultrasonic sensor, I would really recommend going and speaking to those guys. Now, what I wanted to do with the ultrasonic sensor was to do two things. Firstly, I wanted to take it, the output of it from its RS-232 or serial output, rather than utilizing the voltage or the pulse width to go do that. The next thing that I wanted to do was to enable it to do single shot sensing. And you do that on the MB1040 by setting it up and then driving the RX line. And if you drive it appropriately, you can trigger it to do a single pulse out, and it will go and read the data at that point. So that's how I have it configured. You can see that I have the receive line just connected straight into a digital pin on the Galileo, and I take the RS-232 that comes out, and I need to do an inversion of that because it comes out as inverted TTL. The Galileo will read the TTL serial, but it doesn't do the inverted. So I just use a little 2N3904 to go and do that inversion, and that enables me to read directly from the Galileo. I also control the power, and I have a little 2N3906 here that's connected to the 5-volt line, and this enables me to turn power onto the sensor and then effectively reset it. If you read the data sheet for the MB1040, they recommend resetting the sensor after every 15 minutes, I think it is, of runtime. So what I can do with this is just simply control the power and do a sensor reset appropriately based on the amount of time that the sensor has been running. The next thing that I wanted to show you was the I2C port expander that I have, and this is a microchip technology product. It's an MCP 2308008, and that's an 8-port I2C port expander. You can get them as 16-port. 23016 will be 16-port. I only needed 8 ports for the garage door project, so it made sense just to grab that port expander. The port expander takes SCL and SDA from the Galileo, and that's the I2C bus. And you can configure the address of the 4050 by controlling how the address lines A0, A1, A2 here all look. Now, in this particular case, I have them all just tied to ground, so that's the default address for the port expander. And if I needed an additional port set, I could just simply add another 23008 in here and then configure the address such that A0, A1, A2, whatever particular address that I wanted was connected to high, and that becomes part of the address value that I would use on the I2C bus to say I want that particular port expander. Now, this port expander goes and talks to the button array that I have, and you can see the button array in the image. And that button array basically provides a 4-button event source. And we'll go through the 4-button event source when we look at the code that I needed to implement to work with M2 tklib. But fundamentally, the buttons are a select, back and forwards, or left and right, and then a previous. And the previous button allows you to move back in menus. The select button works as either clicking OK or being able to increment integer or text values that you have in the user interface. In this particular case, for the component test harness, I don't actually have any of those controls, so that select button is simply the equivalent of clicking on OK or clicking a button or a link inside a normal Windows application. And these button array are just tied to 4 of the ports, GP2 to GP5, on the port expander. And I can use the I2C bus to go and read those by issuing a command to the port expander and then asking to read the register and check the bit that those buttons are connected to. And they're simply connected and held high. Connected to the through a resistor that enables me to go from 0 to 5 volt. The next thing that I wanted to show was the relay, and in the upper left of the image you can see a couple of transistors, and those transistors I'm utilizing to control the SainSmart 2-channel 5 volt relay, and each of those is a 3904. And basically what it means is that I can drive the 2 inputs, and down here on the relay item you can see IN1 and IN2. And I can drive those 2 values to control which channel comes out. So effectively I have a class that wraps that, and I just tell it which channel I want to trigger, and then it will work out what port it's connected to and then set that port to the appropriate voltage. This SainSmart relay, and you can see it in the image, has an ability for you. It has 2 optical isolators in it. So you can actually isolate the control circuit from the relay circuits directly. And you can configure the jumper that you see there to actually separate those 2 power circuits. I don't have that set here, but if I move the jumper across to the JD VCC pin, what I would need to do then is to actually provide VCC specifically to the output to let the relays act. In this case, I didn't think I needed to isolate the relays. That may change once I put the device in in the control environment when I connect it up to my garage door. But right now, that's all I needed to do. And I utilize the 3904s because that enables me to ensure that I'm giving a positive signal to the relay to say open or close. And I don't have to worry about the floating values or any of the points during initialization to accidentally triggering the relay. What I wanted to make certain was that my relay wouldn't fire in the event of, say, a power failure. When the power came back on, that it wouldn't trigger and say, well, open the door. This way I can be certain that that's going to be the case. Now, the last thing that I have connected to the port expander is the door sensors. And you can see these door sensors up here. They're a Honeywell door sensor. I believe that inside them they're just a little magnetic reed switch. Certainly the control, the trigger thing for them is basically a large magnet. But fundamentally they're acting like a reed switch. And I started with one sensor, but then I realized that I needed to be able to tell the situation of when the door was actually traveling and to deal with the case where the door may need to reset itself. If you've ever had the case where your door hits something, sometimes it doesn't fully open, sometimes it doesn't fully close. If it has a couple of interactions, it'll just stop. And it does that as a safety mechanism. So I wanted to be able to be absolutely certain that the door was either in its closed or open states and react appropriately. So I utilized two of these reed switches coming into the port expander to enable me to tell when the device is closed and when the when the door is closed and when the door is open. So finally, the last thing that I wanted to talk about here is the Galileo, and you can see that I have quite a complex, well, a reasonably complex circuit for driving many different devices. But because I was able to use the SPI bus and the I2C bus, I really don't have that many pins connected to the Galileo. And so I have the ability to do other things with my Galileo. Sometime in the future, as the next projects and so on, once I roll this out into the actual garage, I will look to see what else I can take advantage of on that Galileo. So let's boot the device. You can see the boot screen there, so I can go in and select the first item, which is going to display the distance, and we'll go read the sensor, and then I can stick my hand in front of the sensor and show different distances. Now let's go back and get to the next item, which is to display the door state. So I'll select that, move forward, select that, and now we can see the door state. And I'll take the little magnet and try touching each of the items, each of the sensors, and you can see that when the sensor is red, it changes the door state, and you can see that when there's no sensor, that we're returning traveling. So that's the door sensor. So let's go in now and trigger the relay. And so I'll move forward to the open close door, and I'm going to pulse the relay. When I click the button, we get a little pulse, and you can see the LED flash showing that the relay's come on.